is, got it, recording in progress. And may be familiar with the sort of climate changes that have occurred over this time scale. Other of you may work on longer geological timescales. But this is sort of our starting point, which this is a reconstruction of global mean temperature that was put together by Jeremy Shacken and Sean Marcotte almost a decade ago now, and that's in the blue line. And superimposed on that are the historical global mean surface temperatures in black, and also some future projections out to 2100 for context. And so over this time period, at least according to this curve, we move from the last glacial maximum, which is the apex of the last ice age, warming up over a period of about 10,000 years through the deglaciation. We have some millennial scale climate reversals like the Younger Dryas cooling event. And then we enter around 10,000 years ago into the relatively stable Holocene epoch, a slight cooling trend through the Holocene, culminating in the Little Ice Age around 300 years ago, followed by historical and future warming. And so this curve is kind of framed where we are in terms of recent climate change, but there are a lot of unanswered questions that this curve has sort of brought to bear over the years. One is the evolution of Holocene temperatures. So this is a zoom in of just temperature evolution over the Holocene, and now showing the Shacken and Marcotte data in purple and blue, but then also a more recent reconstruction through the Holocene by Daryl Kaufman's group at NAU, the Temp2L cave reconstruction, which is in green. And you can see it differs a little bit in the earliest Holocene, whereas the Shacken-Marcotte curve, or I'll be calling that SMC for short, shows peak warmth around 9,000 years ago. Peak warmth occurs in Temp12K around 7,000 years ago. So that's one difference. Both of these curves show an overall cooling trend from about 7,000 years ago. And as many folks in the paleoclimate literature have pointed out, this doesn't actually agree with expectations from radiative forcing, nor what climate models tend to do. So this is a figure from a 2014 paper by Liu et al., which compares the trace 21K continuous simulation of climate, which goes from the LGM to present with CCSM3. And you can see that that's the line in black, and that shows you the global climate evolution according to the model. And that's compared here with the proxy reconstruction of Marcotte et al. In blue, as well as an assumption of seasonal bias. So just assuming that many of the proxies are summer biased and what you would get from choice 21K. The takeaway is that these lines don't actually match with the proxies. The proxies in the model predictions disagree. One showing that the Holocene cooled from about 7,000 years ago, and the other suggesting that it warmed. So this is what's called the Holocene temperature conundrum, and we'll revisit it a little bit later in my talk. In addition, none of these existing reconstructions contain any spatial information. So of course, we're used to understanding climate change in global mean temperature terms, but we don't live in the global mean, and certainly some regions experienced larger coolings and warmings over the last 20,000 years plus than others. And until now, we don't have a clear spatial view of what that looked like outside of model simulations. So paleoclimate data assimilation is a way to bring together model and proxy information in a statistical framework and basically leverage the best of both worlds. So models are spatially complete, and they're dynamically consistent. So they can give us full fields of important climate variables like temperatures and wind speed and precipitation. But they are climate models, they're imperfect, they may not always faithfully represent reality. So that's kind of the drawback. On the flip side, the proxy data are recording what actually happened, but they're not always evenly distributed in space or time. And there are uncertainties in the proxy methods themselves because these proxies aren't just passive thermometers, they're usually biological systems. So in combining them in DA, we're trying to put together all the information into one place to get sort of our best kind of hybrid product. So I'll just walk you through the basic DA math, which is is linear. And so in DA, we start with the model state. So the models form your your prior state or your starting state of what you think the past climate looked like. And then of course we want to incorporate proxy information into that. And so for that, we go to a collection of proxy data, and we're going to introduce that into the DA equation as y, as a vector y. We're going to compare the observed proxy value. So in this case, in this example, let's just take a UK37 value and compare it to what the model says UK37 should be for the same location in the model grid space. And so this comparison between y and ye, which is an estimate of the proxy, actually takes place in the native proxy units. And we translate from, in this case, SST to UK37 using a forward model. The forward models in our DA products are all of the so-called Baywatch, Bayesian forward models that we've developed over the years. These are all Bayesian forward models of sort of the major SST proxies. So basebar for TEX86, baseline for UK37, Bayfox for O18, and Baymag for MagCal. And all of these models are available on GitHub, and they're written in MATLAB, but we do have translations for Python for all of them. So these are the models that are used to turn the proxy units, which are climatic units, into our, the model units, the climate units, into the proxy units, so that we can compare y and ye. The difference between what the proxy says happened and what the model said happened is called innovation. And that's the new information that gets added to the prior state. It gets added to the prior state with a weight, the Kalman gain, which I'll explain in the next slide. And then we get a posterior state. So it's actually a linear transformation, addition of new information to the prior state with that very crucial weight. So let's take a look at what the Kalman gain is. Now the Kalman gain, the numerator of the Kalman gain is the covariance between the prior state and the ye estimate. So that's basically the relationship between the forward model proxy value at a certain location and all the fields that are in the prior state, the covariance. And so what that does is it spreads the proxy information beyond its immediate location to other locations, as well as other climate variables. In this talk, we'll be focusing on temperature, but you can put anything you want into the prior state. You can put precipitation, winds, whatever, it all gets collapses into a state vector. And so you can actually inform other climatic variables beyond temperature alone. The denominator is basically the uncertainties. So the variance of ye is the spread and the estimated proxy across the model prior ensemble. And R is the variance, the error associated with the proxy itself, with the proxy that you measure. So if uncertainty is high, the denominator is large, right? And K becomes smaller. And so the innovation is weighted less securely for things that have greater uncertainty. And so this is how uncertainty kind of comes into play when we're doing DA. Now that numerator, here's just a graphic of sort of what it's doing. And I can take myself away here so it's a little bit easier to see. But if we have, for example, a theoretical temperature model, temperature proxy in Seattle, the covariance is just the correlation squared. So it's how much that particular record informs upon the temperature field. So in this particular hypothetical case, you could see a temperature record in Seattle would inform on temperatures across most of Canada in a positive sense, and potentially in a negative sense across the North Pacific. So this is really key because it allows the proxy in one place to inform climate elsewhere. Okay, so this is sort of the math of how DA works. And so let's get into some applications. So I want to start with the last glacial maximum sensu strictu. We chose this as kind of the first climate state that we would try out paleo DA on because we kind of know what's going on. We have really well-known boundary conditions, right? We know that sea level is 120 meters lower. We know the greenhouse gas concentrations from the ice cores. We also have a lot of proxy data for the LGM, arguably one of the best represented paleoclimate times, right? So we have almost 1,000 unique data points, SST proxy data points during the LGM. And so this is showing sort of the underlying proxy data that go into the DA for the LGM proper. This was published in 2020 in Nature. And you can see how many dots there are. Now, I should say that all of the DA examples I'll show you today only use these 4 proxies for sea surface temperature, these geochemical proxies. That is because we have those Bayesian forward models for them. So we have all the pieces of the puzzle to introduce them into the DA. So we didn't include terrestrial data because we don't have forward models for them yet. We would love to add them in the future. There's also some complications assimilating terrestrial temperature data if you're not quite certain what the elevation is, or if the elevation in the model doesn't match the proxy, because obviously lapse rate comes into the situation. So we've been focusing on assimilating SST data so far. Okay, in addition, we need model priors, our starting place. And for that, we're going to use the isotope-enabled community Earth system model, version 1.2, and a few simulations using 1.3. And for the LGM case, my colleague Zheng Zhu, who's at NCAR, developed time-slice simulations of 21 and 18,000 years ago as sort of sampling the LGM state, and then 0 and 3,000 years ago to sample the late Holocene. For the LGM-DA, we binned the data into pretty broad time bins, 19 to 23 and 0 to 4. And so hence the sort of prior states kind of match that broad binning that we took for this LGM-only DA. Now, really importantly, ICSM has isotopes both in the atmosphere and in the ocean. And that's quite important because a good chunk of our data, just going back to the data collection, is the O18 of 4Ms, so 18 of plankton 4Ms. And so obviously we want to leverage that information, and doing so requires knowing something about the O18 of seawater. So having that in the model prior is pretty key. Okay, and so here's the result of our LGM-DA. And so this is a map showing the change in surface temperature in the LGM. And keep in mind, again, this is a hybrid product. So what you're seeing here is a full field, but it's a combination of what the model says that the LGM cooling looked like, but also what the data say that the LGM cooling looked like. And on top, I'm just plotting ice 6G, reconstruction of the Laurentide and Greenland and the Eurasian ice sheet, just for context. So because we have a spatially complete field, we can estimate global cooling very precisely because we have the full field. We don't have to get into the game of latitudinal weighting or scaling from SST to SAT, to surface air temperature. And so from this reconstruction, we find that the LGM was 6 degrees Celsius or about 11 degrees Fahrenheit cooler. So how does that compare to previous work? So going back all the way on the left-hand side of this diagram, some of the earlier estimates of LGM cooling, including the Shotgun estimate from the Shotgun market curve, SMC curve, which is shown here as SH12, were relatively low. So it was only about -3 degrees Celsius for some of those earlier estimates. More recent studies have actually, like ours, been giving answers that are closer to -6, and this includes independent proxies such as the Barretter 2018 study, which is based on noble gas estimate. So it's nice to see that we have some agreement with independent work, and the data assimilation sort of coming in that -6 value, but also is much more precise than some of these other estimates. So the dark blue band here is actually our full range of uncertainty on global mean surface temperature. It's quite tight for this estimate. Now, with this tighter estimate of glacial cooling, what we did in this work was use that to revise our estimate of what Earth's climate sensitivity is during glacial times. So for those of you who are unfamiliar with the term climate sensitivity, what it refers to is the global temperature response to a doubling of CO2 concentrations. And it's a metric of how sensitive the Earth system is to CO2. Now, in models, this is an emergent property, and it can range from sort of a low end of 2 degrees Celsius per doubling out to a higher end of 5 degrees Celsius per doubling. And you often see climate sensitivity appear, as a probability distribution like this, often a skewed one. And so using our new estimate of global cooling, and we can combine that then with the ice core constraints on greenhouse gases and some estimates of forcing associated with the ice sheet, we recalculated climate sensitivity for the LGM in this work, and we did so in a number of different ways, accounting for example, the radiative forcing of dust-based aerosols, mineral dust, in one iteration and leaving it out in another. Also accounting for potential less than one efficacy of the ice sheet in terms of forcing. So that's why there's 3 bars here. These are basically 3 different ways that you could account for radiative forcing aside from that of the greenhouse gases in the ice sheet. But the takeaway is that the central dots represent the median for each of these experiments. And we're getting something between 3.5 and 4 degrees per Celsius doubling CO2, which is kind of right in the sort of expected range of climate sensitivity. And that's an update from older estimates that were using those -3, -4 estimates of global temperature change. And we're getting very, very low climate sensitivity during the LGM. Our estimate brings it back up into sort of the sort of typical zone. And we find very little probability that climate sensitivity is lower than 2.5 per doubling, nor higher than 5 per doubling. And this is an important finding because in the CMIP6 modeling rounds, a lot of the CMIP6 models that were used for the recent IPCC report have a very high climate sensitivity. And you can kind of see in this sort of progressive march between, what the IPCC AR5 ranges for climate sensitivity versus the CMIP5 models that were used in that report versus CMIP6, you can see this red bar is moving up, and a lot of the CMIP6 models are quite sensitive. And so there's been a lot of speculation, whether these models are too sensitive or not, and how much, therefore, we should trust their future projections of climate change by 2100. And you can see here, the LGM constraint definitely rules out some of the higher sensitivities here that are coming out in the CMIP6 models. But to really illustrate that directly, one thing we did with our LGM result is we actually used the proxies alone to get an estimate of global cooling, just taking out the model influence so as not to be circular, and then compared it to runs with different generations of the community Earth system model. In particular, we were interested to ask the community Earth system model version 2, which has a modern day climate sensitivity of 5.3 degrees Celsius, to simulate the LGM. And when we did run CSM2 for the LGM, you can see what happened. The global mean temperature took a nosedive down to a -11 degrees Celsius, which is way outside of the proxy estimate, which is shown here in gray. Whereas CSM1, the model that we've been using for DA, incidentally, is a little bit colder than the proxies, but it looks okay. And interestingly enough, if we just go ahead and replace CAM6, the atmosphere model in CSM2, with CAM5, we can also get a pretty okay LGM simulation. My colleague Jung Soo was able to show in this paper that came out in GRL this year that this is related to the cloud feedbacks and actually just a few parameters that were tweaked in CAM6 that make it a lot more sensitive. In short, this is an easy way to say this model is too sensitive. It can't accurately simulate the LGM, so perhaps we need to revisit some of the physics that are behind that high climate sensitivity. All right, so now I want to move to our most recent work, which is actually creating a continuous reconstruction of climate from the last glacial maximum to present through time now. So what I just showed you before was an assimilation just of the LGM with the late Holocene pair to look at the difference in glacial climate. In this example, we're going continuously with 200-year time steps from 24,000 years ago to present, and we call this product the Last Glacial Maximum Reanalysis, or LGMR for short. And this work is in Press at Nature, so hopefully will be out in the next month or so. Now here's our proxy collection. In this case, we screened the proxies for age control and only included proxies with radiocarbon constraints. And the reason is that in this assimilation, the age uncertainty is one of the uncertainties that is iterated over and included in the reconstruction. And so that kind of knocks down the total number of proxies we have relative to the LGM assimilation, but it's still a really nice collection of proxies, albeit very much heavily biased to the Northern Hemisphere and the tropics. And this is just a function of the data we have out there in public databases, is that the Southern Hemisphere is really underrepresented in terms of SST proxies. And you can really see that coming out here. In terms of the representation through time, pretty good. You can see that the peak is actually during the deglaciation, so reflecting a lot of interest, of course, in the deglacial climate evolution. and that there's a steep drop off towards present day, as of course, many of these are marine sediment cores and potentially missing the most recent time, maybe during coring artifacts and so on. But overall, pretty good coverage. For our model priors, again, we're using the isotope-enabled CSM version 1.2. And now Jung went back, he generated even more model priors for this assimilation for us at 3,000-year time steps from 21,000 years ago to present. In addition, we did some hosing experiments. So we have a sort of Heinrich 1-like hosing experiment at 16,000 years ago. And we also have a Younger Dryas prior. We have during the Holocene a prior that has a green Sahara. We have a prior without a green Sahara. And we have a bunch of pre-industrial priors as well, as you can kind of see that cluster right above my head. So a nice span of model priors to start with for the assimilation. All right, and so this is the global mean temperature that we get out of combining those model priors with our proxy data network. So we're looking at here from starting about 23,000 years ago and coming up to present. At about 2,000 years ago, you'll see a break in the blue line. That is the end. I guess it's more about 1,000 years ago. That is the end of the LGMR. And then what we plot instead is the last millennium reanalysis, or LMR, which is also a data assimilation product that's based on proxy data and model simulation. So we plot that for symmetry. And then finally, at the very end, what is plotted is the HAD-CRU T5 global mean surface temperature for reference. So you can also see that there's sort of a change in time scale here that we jump in time scale just to sort of zoom in and show you the last 2,000 years for context. Now, of course, one of the benefits of DA is we get spatially complete fields. So at top, there are a few anomaly maps of key intervals in time, including the coldest time of the sort of last glacial, which turns out to be closer to 18,000 years ago here than 21. So there's a map there on the left showing you that deep cooling over the northern hemisphere associated with the ice sheets. Fast forward to 12,000 years ago in the Younger Dryas. So we can see that still a cold world, still a Laurentide ice sheet, maybe hints of warming in the southern hemisphere. And then at 9K, you can see the sort of hemispheric differences in warming versus cooling relative to the last 2,000 years. These little histograms there on the left represent the probability of when deglaciation began in a global sense, which is around 17,000 years ago, and when sort of interglacial conditions became established, which is just after 10,000 years ago. We can look at different hemispheric means. We can look at regional averages. And so here's just a breakdown of the temperature evolution of the northern hemisphere in red versus the southern hemisphere in blue. You can see, of course, the northern hemisphere experiences a lot deeper glacial cooling. That makes sense because we have the presence of those giant ice sheets. You can see the Younger Dryas really pop out in the northern hemisphere temperature evolution, but not in the southern hemisphere. And the Younger Dryas cooling, if we look in a spatial sense in the upper left, is really focused in the North Atlantic, North Pacific, and North America. It isn't actually a global event, which makes sense since we know there is this sort of classic hemispheric bipolar seesaw response to that event. You can see it's associated with warming in Antarctica and in the Southern Ocean. We can also do fun things like pull out temperatures, in your favorite town. So for you all, of course, I pulled out temperatures in New Brunswick for the past 23,000 years. We can check it out. Unsurprisingly, the Younger Dryas is pretty prominent here in New Brunswick. Obviously, glacial cooling is very extreme here because we're underneath the Laurentide during the LGM. So we obviously have a pretty extreme glacial story there. But that's kind of a fun element of the LGMR. And we're actually working on building a web interface that will allow people to explore the LGMR and explore, their favorite local town and how temperatures have changed over these geological timescales. All right, in terms of what we can learn from the LGMR about climate dynamics, having the spatio-temporally complete field is really powerful because it allows you to look at the sort of spatial expression of the major drivers of temperature change over these time periods. So to break that down, we went ahead and did an EOF to look at the major modes of climate change in our product. EUF1 is, as you probably imagine, is basically the global warming, the global warming mode. The spatial expression is in the upper left, and the temporal expression is here in the top of this time series in red. And basically, this is, a combination of the major radiative forcings that are contributing to deglacial warming, which is rising greenhouse gases and the ice sheet. So basically the ice sheet effect on albedo. And if we actually take the reconstructed radiative forcing of greenhouse gases and ice sheet albedo and add them together, you get that black line that's on the top graph there. And it looks a lot like, our first mode. So we can understand very simply that the first order driver of temperature change in this time scale is, unsurprisingly, greenhouse gases and the ice sheet. EUF2 is a lot more interesting. So it's a hemispheric mode, as you can see, looking at the loading pattern in panel B there, where there's sort of negative loading over the Laurentide in the North Pacific, North Atlantic, and positive loading in the Southern Ocean. The time series here is this blue line. And there's actually two sort of features in this second EUF2. So we actually kind of broke down that EUF2 into two parts. One, which is essentially the long-term trend, and that's shown on bottom, and another, which is the residual off that long-term trend, which is shown in the middle. Now, the residual of PC2 looks pretty much exactly like the protactinium thorium record from the North Atlantic. And keep in mind that protactinium thorium is not assimilated in this assimilation whatsoever. But really what this element of PC2 is picking up, of course, is the millennial scale events. And so we can see those features corresponding to the Younger Dryas and Heinrich event 1. And maybe if you squint your eyes, you can see maybe an 8.2 or some sort of remnant of it. And so this is sort of one expression of UF2, is that sort of northern hemisphere cooling, southern hemisphere warming that is associated with the millennial scale events of the last deglaciation. The trend is pretty much spot on an insolation related trend, right? So you can match it to any insolation curve you want. It fits well with northern hemisphere insolation at 65 north, but incidentally, it also fits well with the duration of summer in the southern hemisphere. And the reason we looked at that was because if you look at the loading pattern over on the far left on the map, you can see that the positive loading on this mode is really concentrated in the Southern Ocean. And so it doesn't really make sense for this mode to be reflecting northern hemisphere insolation, in which case you would expect positive loading in the northern hemisphere. It's really focused on the southern hemisphere. And so we think this actually gives some support for this paper that was published over a decade ago by Peter Hivers and George Denton, this idea that southern hemisphere temperatures may be very closely controlled by summer duration as opposed to remotely controlled by northern hemisphere insolation. In particular, the loading pattern that we see, that strong positive loading in the southern hemisphere, is kind of a hint that we're looking at a southern hemisphere driven a temperature mode. And in fact, this is, the DA is a reflection of the underlying data. So the underlying data that are kind of contributing to this expression of this mode are sites like this. This is an Alkanon reconstruction of SST near New Zealand. And you can see that it's very warm in the early Holocene and very warm very early in the early Holocene, sort of peaking around 11,000 years ago. And that is the sort of peak of that insolation-driven component of UF2. So UF2 is a superposition of two things: the millennial scale events and the impact of orbital forcing, and particularly on southern hemisphere, Southern Ocean warmth, which we found to be pretty cool and interesting to find. All right, so I want to shift into the Holocene now and revisit this conundrum issue. So as a reminder, the problem is the model, in this case, trace 21K, but other models as well, tend to show, a warming trend through the Holocene, mid-Holocene being slightly cooler than the late Holocene. And that's not what previous reconstructions of global mean surface temperatures indicate. They tend to show the opposite. So what does the LGMR have to say about this? Well, in the LGMR, the conundrum is gone. In fact, we see a pretty decent agreement with the trace model simulation. So look here at these lines on the bottom in blue, we have the trace model simulation in dark blue and the LGMR evolution of Holocene temperatures in lighter blue. And they're not exactly the same. You can see, for example, that the LGMR has pretty strong warming up to about 8,000 years ago when the Laurentide then decays, and less strong warming thereafter, but it has a warming trend from 7,000 to present, much like trace does. And so that's really different from the red curves on top, which include the SMC curve, as well as temp 12K, which again show that cooling trend from 7,000 years ago. So conundrum is gone. The LGMR does not show conundrum. And of course, we had to find out why. Why did it go away? So starting at the beginning, we first looked at our proxy network to make sure that it wasn't just the fact that we're using a bigger collection of proxies. And we found that it wasn't. In order to do that, we created a classic proxy-only reconstruction. So no assimilation, just based on the proxies alone. And that's what you see on the upper panel here in red. The dotted line is the SMC, shotgun market curve. And you can see we get a very similar answer as they do, just using a conventional proxy-only reconstruction approach. We actually do get Holocene cooling. Okay, and again, the LGMR doesn't show that. It shows fairly flat, but actually a slight warming trend through the Holocene. So it's not the fact that our proxy network is bigger. It's not the model prior, so it's not necessarily coming from the models, because our model prior actually allows for a warmer mid-early Holocene. You can see that in our 6K priors in particular, there's a spread. It could allow for a warmer Holocene solution. So this isn't something that's baked into the model prior. So then, of course, we had a look at seasonality. So Samantha Bova, Yer Rosenthal, and colleagues recently published a paper suggesting that perhaps the conundrum is really just comes down to seasonal bias in the SST proxies. After all, many of these proxies are based on biology, and biology tends to grow seasonally. And so they propose that as a solution. So we wanted to investigate the role of seasonality in the LGMR as well. Now, as a reminder, our proxy system models, the Bayesian models, are all seasonally resolved. In particular, for the 4M-based models, seasonality is built into these forward models. And so this is a figure from the Bayfox paper in Paleo. On the left, what you're seeing is kernel density estimates of the abundance of G. ruber and pachyderma in sediment traps, in a global sediment trap collection. And you can see that, G. ruber, pachyderma, they have thermal tolerances that they're associated with, and they sort of reach max abundance at a certain temperature. So from these sorts of analysis of the KDEs, of the abundance of these species, we define 90% confidence intervals for their thermal tolerance range, which you can see there in dotted lines for G. ruber 22.5 to 31.9. And then we assume that, if SSTs are outside of that optimal range, that probably the species would be growing on a seasonal level. So these cool looking diagrams here, which remind me of kaleidograph or something, or of those toys that you grew up with and making all the spirals, are showing you the assigned seasonality of G. ruber in different areas in the modern and the tropics, because of course temperatures don't have a huge seasonal range. In general, G. ruber will be, we assume, growing year round. But if we move into the extratropics, then you can see that the lines are assigning the seasonality to the summer seasons, respectively. So this is all built in to our reconstruction. And in fact, the seasonality can evolve through time in the DA context because everything is done in proxy unit space. So we grab our model priors, look at the seasonal range in SSTs, and then decide what the seasonality of each 4M should be through time, which means that the 4Ms can actually change their seasonality in the reconstruction. So one way we want to check the influence of seasonal is to freeze that dynamic seasonality in the data assimilation framework and assess whether there's a difference if we essentially turn off seasonality in our forward models. Okay, so this fan of colored lines shows you a bunch of different experiments that we did to look at this, testing the sensitivity essentially of our forward modeling assumptions to seasonality. Now, UK37 has a really basic seasonal model. We only assume that it's seasonal in the North Pacific, North Atlantic, and Mediterranean, which are places where baseline suggests that seasonality occurs today. And the takeaway there is those two red orange lines look really similar, whether we just use mean annual records or seasonal records, we get the same answer. The blue lines show experiments with the 018 forams. So the darkest one is our standard DA. And then we fix the seasonality at what it would be in the pre-industrial, what it would be in the LGM. And in short, we didn't actually get really much difference when we did that, especially in the Holocene. These dotted lines show examples where we took away the species-specific forward models that we have in Bayfox and just lumped all the species together. And that, again, surprisingly, didn't have much of an impact. So basically, whatever we did to 018, we basically got the same result. And I should mention these are proxy-only DA. So we only did DA with 018 as experiments. And MAG-Cal, you can see that there's a little more action going on here. Although, again, when we fix seasonality at pre-industrial and the LGM, we didn't get too much of a change. Fixing at the LGM reduces the magnitude of Holocene warmth in the MGCA DA alone. Unsurprisingly, when we use the pooled species models, so taking away our species-specific models, which are tuned to Beloides, Seculifer, Ruber, we get a pretty crazy result. We get a really warm early Holocene if we don't account for species-specific differences in MAG-Cal. And so that really drives home the importance of having species-specific calibrations for magnesium calcium data. It also, though, proves that the solution that we have in our full DA is not baked into the model prior, because we can get a very strong early Holocene warmth if the proxy said that that was what was happening. So our takeaway from this is actually that the seasonality isn't the explanation for why our conundrum is going away, because in many of these experiments, freezing seasonality actually didn't do much to the answer. You will, however, note that since as these are proxy-only experiments, that each proxy looks a little bit different, right? That the 018 data tend to suggest a cooler, earlier Holocene. UK is pretty flat, and MAG-Cal is warmer. So there are some sort of proxy-specific differences here. Now, none of this is to say that seasonality doesn't matter. It's just that to the extent that we have tried to build that into our forward models, it doesn't explain what's happening with the conundrum. So as next step, we looked at the impact of data in different regions. So this shows the proportion of records by latitude. So they're coded from the Southern Hemisphere in 15-degree latitude bins up to the Northern Hemisphere. As a reminder, you can see that the bars, the cool bars, are very low. We don't have many records in the Southern Ocean, not as many as we would like. In this context, what we did is we systematically left out different 15-degree latitude bands to see the impact on both a traditional proxy-only reconstruction and also data assimilation. In the proxy-only space, which is the solid lines here, it didn't really matter for most of the regions whether we left out proxies from them, except for the southernmost region of 45 to 60 degrees south. You can see that that blue line there has much lower temperatures in the early Holocene. It turns out the data in this latitude band can account for about half of the Holocene conundrum alone. And the reason for that is even though there are relatively few data in these bands, they have a warm early Holocene, as I showed you earlier in the talk. And in a traditional proxy-only reconstruction, that band gets equally weighted with similar latitudinal bands that have more data. So effectively, those records get upweighted into the global average. In the DA context, it's a different story. Leaving out that southern band actually doesn't change temperature evolution so much. In the DA context, the band that matters the most is actually the red band. And when we leave it out, we get a little bit of a warmer, earlier Holocene. And that's because those records in the high northern latitudes are feeling the Laurentide and are typically colder in the early Holocene as the Laurentide is still present. So there's a little bit of a smoking gun here in the sense that we think some of the conundrum could be explained by upweighting of Southern Ocean records in the proxy-only reconstruction context. But there's not a single thing that's contributing to the conundrum. And there's not a single thing that's contributing to the fact that it's gone away in the DA. But we think the most important thing is the way that DA weights the proxies, right? It's based on physics. It's based on how much a proxy in a certain location affects SSTs around it based on the model covariance structure. And that weighting is a lot more sophisticated than just straight latitudinal weights. So we feel confident that our solution of a very small but statistically significant warming through the Holocene is correct. All right, so now just some context for present day warming. So looking again at our global curve, one of the things that really stands out about this curve is that it's very clear that the most recent warming in the most recent decade, 2010 to 2020, far exceeds any sort of values of global mean surface temperature we've seen in the last 24,000 years. And it's in the 99, just exceeds every percentile. This is an ensemble-based reconstruction. We have 500 member ensembles. We've sampled age uncertainty, all the proxy uncertainty, and so on. And just any way you cut it, modern warming is far above this. So we can truly say that the current temperatures are unprecedented in at least 24,000 years. We can also say something about the rate of current warming. And for this, we tried to focus on centennial scale weights of warming, because after all, the resolution of the LGMR is 200 years. And we're iterating through different age models as we're putting it together. And many of the records actually have a temporal resolution that's smaller than 200 years, but nonetheless, it's not an annual record. So to make this more of an apples to apples comparison, we looked at the rates of centennial scale warming in the instrumental record on the left. And so just stepping through every 10 years and calculating the rate of warming starting in 1850. And then we compared those warming trends to a couple of different estimates of the rate of deglacial warming in the LGMR, which of course is when the fastest temperature changes are occurring. And so you can see there's three different distributions here. The light gray one is straight up from the LGMR ensemble solution. The dotted line is actually a decadal resampling that we did to sort of mimic the noise that we would experience if we could actually resolve the LGMR on a decadal level. And you can see that sort of spreads out the distribution a little bit. And then we went ahead and plotted up trace rates of deglacial warming, because trace is resolved on the annual level. And you can see it's reassuring, it actually looks very similar to the LGMR. Nonetheless, that the takeaway is that this red line, which is the rate of warming from 1920 to 2019, is basically in the tails of the distribution, the far tail of the distribution from what we get in the LGMR, which leads us to conclude the rate of warming, in addition to the absolute temperature level, is unusual in the context of the last 24,000 years. Great. So with that, I want to acknowledge my team that is behind the LGMR and the LGM data assimilation. We've been working on this since 2015. So this is a 6-year journey, and it's been an enormous amount of work to compile the proxy data, to run the model simulations, and then build the statistical framework. So I have to thank my former postdoc, Brewster Malovich, who now works at the Rhodium Group, my PhD student, Jonathan King, who built the DA code from scratch. It's called Dash and available on GitHub. Zheng Zhu, who put together those beautiful model simulations for us. And finally, Matt Osman, who's a lead author on the LGMR, and in the last 2 years has been putting all the pieces together. So thank you very much, and I'd be happy to take some questions.
Thank you, Jess. So as usual, feel free to just chime in and ask your question. If you'd rather submit it in the chat, I could also read it as well. But yeah, the floor is open for questions.
I'll jump in if it's okay. One of the things I love about, great talk, by the way, really covered some ground that I've been thinking about very hard lately. And one of this is this Southern Ocean, Northern Hemisphere sort of difference in time in terms of timing of deglaciation and who started first and what's leading. And so one of the things I like to point out or like to think about is like, the bowling aileron to me is the Antarctic cold reversal. And one of the things that jumped out at one of those simulations early on is, or your northern southern hemisphere, that I didn't see a real ACR or even kind of a pause. A couple slides ago where you were looking at those two different, so yeah, but why? Yeah, a little bit further back actually. I'm looking that one, right? There's no ACR. what's your theory on that? I mean, these models can't get everything, but I'd be really curious.
Yeah, that's a great point. There is no clear ACR in the Southern Hemisphere average. I haven't looked at, this is the whole Southern Hemisphere average.
Mhm.
So it might be worthwhile for me to look at the Southern Ocean average,
Right.
where you might see the ACR expressed a little bit more clearly. I should say we didn't assimilate ice cores. We actually held them out as independent validation where, again, the ACR is really well expressed. But we did, let's see, we did compare to the ice cores, and I'm just going to check there. And so this is,
Sorry.
oh, no worries.
Scam call right at the right time, of course.
Yeah, so this plot is actually showing the LGMR reconstructed 018 of precipitation in red compared to the observed, the observed trajectory, which is in this red dotted line. It's a little hard to see in the model prior. But I'm seeing that actually the Antarctic cold revulsor does show up in our reconstructed 018, and you can see how good the match is, especially with East Antarctica. And so this is actually, to us, very impressive because, again, the ice cores were not assimilated. So this is the LGMR giving its best ice core attempt, and it's doing an excellent job with the Antarctic ice cores. It's less good with Greenland and less good with the Spithens, but so there is an ACR in the product. It just
gets kind of melded out.
It's probably really focused around Antarctica in the Southern Hemisphere. And so if I took like a more regional average, you would probably see it. But I was going to comment that, yeah, in terms of the spatial, we did look at kind of like where the earliest deglacial onsets occur. And we did find that they were in the Southern Ocean.
That's what I'm seeing in my data for sure.
Yeah, so that matches the underlying data, including your records, which are in the DA. So,
Oh, thank you. But I've got some time talking with you later. We can take this nitty-gritty stuff off. I see some questions in the chat that you should answer because we're going to have time together later.
Yeah, should I read the question in the chat?
Yeah, I can go ahead and read it. So essentially, you mentioned earlier about the lower data coverage of your SST records in the Southern Hemisphere. Are there any ongoing efforts to improve that coverage?
Yeah, so I mean, this is, again, our data set is, what's publicly available in Pangea and the NCDC, what's been published. I see there's kind of a two-part question here. So in terms of the resolution, yeah, we did have criteria for temporal resolution, but for the Southern Ocean, we relaxed that. We basically took anything and everything we could find, regardless of the resolution, although we did require that it have radiocarbon dates. And so that allowed us to at least include some more data from the Southern Ocean in that way. But yeah, I mean, again, I feel like Liz is the person to ask about this since she's been working in that region for so long. But my understanding is that, it's really challenging to get cores in the Southern Ocean in the right place with sedimentation rates that are appropriate to reconstruct climate on these timescales. And so I think, it's just kind of like, this is what we have. And I mean, I guess, yeah, like our paper just highlights, like we should prioritize trying to recover more data from that region. It's a very important region.
Stay tuned. Ryan's hot on the trail.
Awesome.
All right, you got a couple more questions here in the chat. The first one is, what are the prospects of applying this kind of DA approach for rainfall reconstructions?
Right, so actually we do have rainfall in the data assimilation in the LGMR. So we can include it in the prior state, and we can then get a posterior rainfall distribution that is nudged by the SST data, which is not entirely crazy, especially because the patterns of SST over the ocean are very, very closely linked to, for example, the location of the ITCZ and the configuration of the seasonal monsoons. And so we can indirectly get precipitation information from our assimilation. We did not include those fields in this paper. We will be releasing them with sort of the caveat that we haven't validated them, and so we don't know how correct they are. They're physically consistent with SST data, but we will be releasing them. Of course, I mentioned that we didn't assimilate ice core data, we didn't assimilate caves. We kept them aside as a check, as a validation check. But we, of course, could assimilate these sorts of data, for example, the terrestrial archives of the isotopes of precipitation. And that would be a really powerful way to improve the reconstruction of hydroclimate over land. So we didn't do that in this product, but we absolutely could. And that would probably give us more constraints over changes in rainfall patterns over the continents.
Another question here, were you able to see with your results what factors like CO2 or volcanoes were most significant contributors to the warming?
So in terms of deglacial warming, it's basically our EOF1 mode essentially identifies it as almost a linear combination between greenhouse gas forcing and the change in albedo from the ice sheet. So I can go back to that slide. So that red line on top. So greenhouse gas forcing, that's basically the change in CO2 and methane. And so that's like the primary driver. But basically, the ice sheets in the Northern Hemisphere are really big. They're reflecting a lot of energy. And so the change in albedo is fairly strong. And if you break down the watts per meter squared forcing of greenhouse gases and the ice sheet in the last glacial maximum, it's about 50-50 if for each. So the ice sheet is equally as important as the greenhouse gases in driving glacial cooling. And then the decay of the ice sheet is equally important in driving the glacial warming. Of course, the decay of the ice sheet is ultimately driven by the greenhouse gases. So what we're seeing is essentially a feedback, right? The ice sheet is essentially a feedback driven by greenhouse gases. Of course, there's the orbital forcing is the change in the precession cycle. And so while that matters for the seasonal changes, it actually cancels out in the annual mean. So it's not very important on these timescales. So basically the main driver is greenhouse gases.
Great. Any other questions? What's the rule? It's 8 awkward seconds of silence before you call it.
Can I ask another question on a completely different topic? The whole Holocene conundrum. I think it was the Marcotte 2013 paper. You showed some of the plots from that, and I totally agree with what you're saying. But I got out of that paper from almost 10 years ago now that the problem with the conundrum was there was a few Northern Hemisphere records that were kind of overweighting that. And that's not what you're saying here today, are you?
Yeah, so in particular, and I know you're probably familiar with these records, there were Julian Sachs Alcanal records from the North Atlantic have a huge change in UK 37 across the Holocene because they're essentially recording the changing Gulf Stream Labrador current boundary. And yeah, so if you take those out of SMC, it drops the magnitude of that early Holocene warmth by a non-insignificant amount, but it does not take it away. And I should also say that we left those records out of our assimilation. And the reason is because our model doesn't put the Gulf Stream in exactly the right place. So you get some weird stuff happening when you try and update the model, but the Gulf Stream isn't right in the right place. So we left them out. So taking those records out, they're also out of our proxy only reconstruction, which is the lightest red here. You can see it's still there. The early Holocene warmth is still there, even with those 2 records kicked out. So although I wanted that to be the easy solution, it turns out that it's not. So.
Which just says that, how significant this sort of, with the modeling that you're doing in this data assimilation in picking apart these flyers and flyers or flies in the ointment or whatever. So yeah, no, this is just really excited to see this coming out. Thank you.
Yeah, no problem. Thanks.
Raphael asks, how big is the innovation on the SSTs, and could that be introducing energy into the system?
I'm not sure I totally understand the question, but perhaps it might be linked to, okay, so the data assimilation technique that we're using is offline. I didn't specify that, but it's entirely offline, which means that unlike data assimilation that's done for reanalysis projects, like, yeah, okay. So there's no potential for the model radiative balance to like reset. Yeah, so no, not in this case, because it's and the reason for the offline is like pretty simple. It's just that, we can't hang out on Cheyenne and like just keep ICSM running. It's like, they wouldn't let us do that, right? So it's more like out of convenience that all of our paleo DA stuff is offline at this point, just for computational reasons. So
Great. Okay, well, we're at the end of our time. Thank you all for coming. Yeah, Jess, that was a great talk. Thank you for all of that. And yeah, I believe you have, I think, 15 minutes to cool off before your next meeting.
okay, thanks, Ryan. Yeah, I'll take a break and then I'll jump on the other Zoom link.
Awesome. Thank you.
Thanks again, Jess.
So
This is
much.
great.
I really enjoyed the listening.
Thank you.